Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Satyajit Thakor, and he will be speaking on the undirected multiple unicast network information flow problem. Dr. Satyajit Thakor joined the School of Computing and Electrical Engineering at the Indian Institute of Technology, Mandi in January 2014, where he is currently an associate professor. Prior to that, he was a research assistant and postdoctoral fellow at the Institute of Network Coding, the Chinese University of Hong Kong, from October 2011 to January 2014. He received the BE degree in Electronics and Telecommunication from Dr. B.Eng University, India in 2004. He received the M.E. and Ph.D. degrees in Telecommunications in 2006 and 2012 from the University of South Australia, respectively. His research interests include information theory, network coding, and algorithms. Dr. Satyajit Thakor is a recipient of the Teaching Honour Roll Award of IIT Mandi for excellence in teaching, the Michael Miller Medal of University of South Australia for his PhD thesis, and the Endeavour Research Fellowship of the Australian government towards a research visit to the Chinese University of Hong Kong. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Satyajit directly. Over to you, Dr. Satyajit.
Thanks, Anushri, for nice introduction. And hello, everybody. I'm Satyajit. I thank CNI Network Seminar Series organizers for this invitation. And today I'll give a talk on undirected multiple unicast network information flow problem. So if you have any questions, just let me know. Either you can interrupt me or put in chat box, or even you can email me later if you have any questions of interest later. So for today's talk, this is the outline. So we will start with some basic information, that is background. So we will just try to understand the idea of routing and network coding with very simple examples. And then we will see communication in directed and undirected networks. Then we will see an important conjecture about network information flow in undirected networks, particularly for unicast case. So after that, we will go into a bit more mathematical detail, and we will discuss, we will see what network models are, directed and undirected network models. Then we will see network coding. We will review what network coding is. Then information inequalities. So information inequalities are very important for obtaining converse type results. One of the result is converse type here. So we will discuss information inequalities and some known bounds for information flow in undirected unicast networks. Then we will see one of our main results, that is partition bound. So that is a bound on the network information flow. And then we will discuss the problem of computing this bound. And also we will see some classes of networks for which this bound is tight. This partition bound is tight and is achievable using routing schemes. And then finally, we will see a result on set of networks, and then future directions as well. So let's now move to the first slide. So let's first discuss communication in a directed acyclic network. So we'll start with one simple example. So first, we are interested in directed acyclic butterfly network. And then assume that in this network, the capacity, H capacities are unit capacities, meaning that each edge can carry 1 bit of information per use. I mean, for a given time instant, it can only communicate 1 bit of information. Now the question is, can we route 1 bit of information for each session per network use? Is it possible or not? So here we see that here is a source, one source that is at this node, this source is available, and this source is demanded at this node. So that is called sync node, and it is demanded here. And here is our second source, and that is demanded here. So this is the communication problem we want to solve. We want to make sure that information available at S1 reaches to T1, and information available at S2 reaches to T2. So if we want to route information, then you can see that there is only one directed path from S1 to T1. This is the directed path, and for S2 to T2, it's the same situation. There is just one directed path. So we can see that if we want to use network once, meaning that each edge is used once, because of this bottleneck, we cannot send 1 bit per session through this network using the network once. So you can only send a half bit each, and we can fully utilize this bottleneck edge, and then half bit can reach. Or in other words, you can use this network twice. So in the first network use, you send information from S1 to T1 1 bit. In second network use, you send S2 to T2 1 bit. So basically we are sending 1 bit using networks twice, meaning that the information that we are sending is 0.5 bits. So basically we cannot send more than 0.5 bits in this network due to this bottleneck. So now, can we actually communicate more than? An important question that we can ask ourselves is, can we communicate more than 0.5 bits per network use or not? So answer is yes. So to communicate 1 bit per network use per session, we need we cannot do it by routing. We need more sophisticated communication scheme. So that is called network coding. So let's consider again the same network, but we will encode information within network, so that to ensure that we can communicate 1 bit per session per network use. So again, S1 is a source, first source, and let's say B1 is the message or the bit that is available at S1. And S2 is another source, and B2 is the bit or message available at S2. So S1, again, it wants to send that information, that B1, to this node. So we want to make sure that B1 reaches here, and S2 wants to send B2 here. So we want to make sure that B2 reaches here. So here is a scheme, a network coding scheme that shows that we can send 1 bit. How? So this source will send B1 bit from both the edges here, and this source will also send B2 by these edges. Now at this intermediate node, this node will, rather than just sending B1 and B2 separately by using different time instance or use of network, it will encode it and send a function of it. So here consider that it is sending XOR function of this 2 bits B1 and B2. So that is, this function is 1 bit, so it can it satisfies the capacity constraint for this edge. And this node basically replicates this function and sends it through both the edges. So now if we at T1, if we just XOR this information that is received and then this message that is received, then we can recover B1. And here also, if we XOR this B1 XOR B2 and B1, then we can recover B2. So this is the basic idea of network coding, and that was given in this paper, network information flow. So now we see that using routing, we can send 0.5 bits. Using network coding, we can send 1 bit. And here I like to say that we cannot send over 1 bit. Okay. So there is a converse type result for this network that shows that we cannot send over 1 bit. So now we have achievability scheme and we have a bound that matches. So capacity for this network is 1 bit. So now let's understand one more concept, that is rate advantage. So we are talking about routing and network coding. So whatever is network coding capacity and its ratio with the routing capacity, so that is called rate advantage of network coding over routing. So in this network, we have seen that this advantage is 2. So first we note that this rate advantage will always be 1 or higher, because routing is just one special case of network coding. So whatever routing can achieve, network coding can also achieve. The question is, can it be strictly greater than 1 or not? So in this case, it is strictly greater than 1. So now we move to undirected network. So first we have seen directed network. So now in undirected network, again we have a butterfly example, but now edges are undirected, meaning that information can flow in either direction subject to the edge capacity constraint. So now in this network, can we route 1 bit per network use or not? So the answer is yes. So basically we have seen that for directed acyclic network, it was not possible for that butterfly network. Here it is. So for example, we can see that if we send half a bit of information from S1 via this path and half a bit of information via this path, then 1 bit of information can reach here to T1. And if we now we know that for this edges, half bit of capacity still remains. So that is a residual capacity we can still use. So for that, if we send half bit of information through this path and half bit of information through this path, then we can get 1 bit of information from S2 to T2. So we can see that here a routing can achieve 1 bit of information per session per network use. Now,
can I ask a question?
Yes.
Okay. So in this undirected case, what is the meaning of capacity of an edge? Is it the summation of the thing of amounts that you can carry in each direction?
Capacity of network for this is just means that see, for undirected edge, information
capacity of
can
just one edge, not network.
Hello.
Capacity of an edge.
Hello.
Yeah, I'm asking what is the definition of capacity of an edge in this undirected?
Yes. So capacity is just some number, positive real number. Okay. And then the basic idea is that whatever, so random variable flows through the edge. Okay. So that the entropy of that random variable cannot exceed that positive real number. That is the capacity.
Yeah, but is this the flow? Are we considering in both directions, or this is?
Yes. So for undirected case, in either way you can send information, but the total capacity that you can use. So whatever. So for undirected case, there can be bunch of random variable flowing in either direction. So that some of that capacity cannot exceed.
Okay.
capacity, that real number.
Okay. All right. Thank you.
Yeah. Okay. So now we have seen that for undirected butterfly network, routing can achieve 1 bit of information. Now, can we do better for using network coding or not? So that is the question. So answer is that no, we cannot have, by using network coding, we cannot improve upon routing capacity. Okay. So the basic idea, again, there is a converse result that says that you cannot pass more than 1 bit of information here. So some of those converse results, like cut set bounds called sparsity bound, we will see in the coming slides. So you see that network coding is useful in directed acyclic networks, but for this case, at least for butterfly network, we don't know whether network coding can improve, has any rate advantage or rate benefit, right? So this example raises one very important question. So that is this conjecture, that is the central part of this talk. The conjecture says that network coding has no rate benefit over routing in undirected multiple unicast networks. So multiple unicast just means that there are multiple sessions in networks, and unicast means that each source is available at some one node and it's demanded exactly at one node. So that is a unicast scenario. Okay. So this conjecture was given in 2004, and it's still open problem. And of course, the problem itself is of interest by itself, but it has many implications as well. In communication, of course, if this conjecture is true, then we need not look for better. We should not go for looking for better network codes. However, it has even found implications in theoretical computer science problems. So using this conjecture as a assumption, recently some authors have shown that they have obtained a lower bound for external memory integer sorting via network coding. So they have shown the complexity lower bound for that algorithm. Okay. So there can be other important implications which are yet undiscovered. So in that sense also, it's a very interesting problem. So now question is that if we can characterize the capacity of information flow or network coding for undirected networks, and if it matches the routing capacity, then we have proof for this conjecture, correct? So in that direction, we try to upper bound the information flow in undirected networks and get some results based on that. So as I said, so far we have just tried to understand routing, network coding, directed acyclic networks, undirected networks using examples and that conjecture. Now we will see in more detail, in mathematical detail, the models, and then what network coding is, its a precise definition, and some notions. So we will see that, then information inequalities, and some bounds, and then the some new results. So let's start with a mathematical model for networks. So undirected multiple unicast network, so that is G, can be given by 6 tuples. So the first is this set of nodes, and second is set of edges. Then we have I, that is a set of sessions in the network. Then there are two mappings, S and T. What are these mappings? So these are mappings from set of sessions to nodes, and Basically what it means is that SI, so ith session, SI means that the node where the source or the information for session I is available. So SI is that node, and TI is the node where the information of ith session is demanded. So that is just source sink mapping. And lastly, we have edge capacities for each edge. Okay. So so as we go forward, we will just simplify the model. We will just consider unit capacity networks. Then we can drop this notation of capacity. So similar to undirected networks, we have notation, or we have model for directed multiple unicast networks. So it is very similar. We are just representing this graph with a vector notation. And then edges, the node set remains same, notation for that. Edges are again directed, so we are using vector notation here. And edges have this form. So edges are of form UV, and here the order matters. So here it means that this edge is from U to V, meaning that U is its tail node and V is its head node. And for undirected case, this order does not matter because it's just an undirected edge between two nodes. So this is network model. So now let's see, for each session, we have associated random variable or message. So we will denote random variable and message by same notation, and it should be clear from context. So here yi is that random variable, that is the random variable associated with session I, and it has alphabet which is calligraphic AI. So model assumption is that all yi's are independent and uniformly distributed. All sources are independent and uniformly distributed. Then we have random variables or messages flowing in edge, directed edge. So that is represented by U subscript E or U subscript U arrow V. Okay. So as I said, for directed edge, U is basically tail node of E and V is head node of V. So now a few more, couple of more notations, and then we will see what the notion of network coding. So for subsets V prime and V double prime of V, these are just basically bunch of edges. Okay, so this notation means that all the set of all edges such that the tail node of E is in V prime and head node of E is in V double prime. Okay, and if we, this double arrow just means that we union both of these sets. Okay, so given that the random variables or messages flowing in this set of edges is denoted by this. So this is simply a random vector. So this is a vector of these random variables. Okay, so now we arrive at a network coding problem. So network coding problem, for first we will just consider directed acyclic graphs. Network coding problem for this directed acyclic graphs or networks, and then we will see how we deal with cyclic graphs and undirected graphs. Okay, so for a network coding problem is specified by non-negative real numbers DI. So these are the demands. So once you specify demands for each session, then we have a network coding problem. So once we have that, then we can look for a network coding solution for that problem. So here is the definition, general definition of network coding. So network coding solution is specified by these conditions. So basically these are two conditions, encoding and decoding conditions. And encoding condition says that for each edge, the encoding function, so this is actually a composite function, so is computable from the functions or messages on edges that are incoming to this edge, and all the source random variables that are available at the tail node. So simply just it means this, that in a network there is some node, let's consider that node and this edge. So let's say this is the edge. It's not working. Okay, so this edge, let's consider it as a, it's working. Yeah, now it's working. So let's say this is edge E. Okay, so it means what this encoding constraint says is that if that whatever message we want to pass through this edge has to be computable from the messages that we receive from this edge. So let's denote it, this edge, by E prime and this by E double prime. Okay, and the source message that may be available at this node. So let's say here we have a source message available, that is yi. Okay, so that's what actually means. And for each session, the decoding function is this one. So again, it just says that let's say consider a node that is a sync node. So let's say that this is Tj. So at this node, we want to make sure that we want to decode the random variable yj. So this yj must be constructible, or we should be able to compute it by random variables that are incoming to this that are incoming to this node. So that's what it means here. Okay, so this is the definition of network coding solution. So once we have a network coding solution, then we can have, okay, I think the screen has got frozen, so not sure. Okay, so this needs to be restarted, so please bear with me. Yeah, are you sure it won't work? Okay, so this is a new virtual class system, and then I'm not sure that there are some issues that needs to be worked out. Anyway, let me just summarize what we have discussed. We started with idea about routing and network coding, and we have seen that network coding has a great benefit when we consider directed acyclic networks. But when we consider undirected networks, it's still unsolved problem whether there is rate benefit or not.
So one question, can I ask one question in between? Hello, Satyajit, can I ask a question?
Yeah, sure.
Okay, so the network coding problem that you mentioned, the solution is there could be multiple solutions, right? As posed. So is there any notion of a best or an optimal solution in some sense, which you are looking for, or any solution would be okay?
So the question was that is there a notion of optimal network code? So we will see that. So given a network coding solution, it has some rate. If we have all network coding solutions we consider, and if we want to, if we get for all those rates that can be obtained for those network coding solutions, supremum of it is the network coding capacity.
Okay.
So let's see that. So network coding now let's see the rate here. So given a network coding solution with finite alphabets, its rate is the maximum value R that satisfies these two constraints. So that is the definition of code. So basically, it just means that it must satisfy the capacity constraint as well as age capacity constraint as well as the demand constraints. Okay. So now we just focus on zero error capacity, not the traditional idea of vanishing error capacity. So for a given network coding problem, its zero error capacity is defined as the supremum of rates over all possible network coding solutions. So this simple proposition says that for a given network coding solution with rate R, these constraints must be satisfied. So it has a very simple proof. You can go through this reference to know more. But basically here the parameter, this log B, is a normalizing parameter. It just reflects that log B times we have to use the network to make sure that this network coding solution is used. Okay. So now let's move to cyclic and undirected network. So as I said, network coding that we have seen, or the definition that we have seen, so that is for undirected, directed acyclic networks. But here we are concerned with network flow in undirected case. So for that, cyclic and undirected networks, the important thing is to ensure causality or time dependence in network coding solution. So of course, information can flow in both directions or even in cyclic way. So now causality is very important. Otherwise, we cannot have a realistic or implementable network code. So otherwise, what happens is that the resulting solution, network coding, is invalid in a sense that there are circular dependencies among messages transmitted through edges, which cannot be resolved into a sequence of time-dependent transmissions. So such invalid network codes are called chicken and egg solutions, which are invalid basically, and because of this circular dependency, if they are not implementable. And to ensure causality, what can we do in undirected network? So some authors have given idea of considering a time expanded network. So once we have undirected network, we convert it into a bidirected form, and then the bidirected network we convert into a time expanded graph. And in the time expanded network will always be directed acyclic network. So now we can safely define a network coding problem and network coding solution that is causal. So let's see that. So again, I'm just giving the idea in a very basic way. So here is undirected network that we have seen before, butterfly undirected network. So we can convert it into bidirected form. So we have simply replaced each edge with two edges in either direction. So this edge and this edge. And the capacity constraint is that the total capacity of this two edges is same as capacity of this. So there is in either direction you can send information in a variable way. So but the only constraint is that the total capacity is less than the capacity of this edge. So this is bidirected version of undirected network. Now we can go to the time expanded network. So here is the time expanded network for this butterfly network. So what is time expanded network is that in the original, in the bidirected network, if there is an edge from one node to another, then that edge is from kth time index of that node to the k+1 time index of the head node in the next layer. So in that way, this is constructed. So you can see that here is layer 1. And if there is an edge from this node to this node in bidirected case, so that edge actually goes to the that node in the next layer. So that way we construct this time expanded graph. Here I am just showing the graph for 4 up to time instant 0 to 3. Okay, so this we can have a time expanded graph with any number of times we can do this, and we can have directed acyclic graph. Okay, so now let's see, without going into much detail of this time expanded graphs and how network coding is defined on it. I mean, how the capacity is defined for undirected. The network coding and rate defined for undirected networks. We will just try to understand in a summary the whole idea. The network coding problem on time expanded network we can now safely define, because it's a directed acyclic network. There is no causality issue. Then time expansion parameter is let's denote it by lambda, and this is not fixed. Okay, so in the previous slide I have shown one example. So there the lambda parameter value was 3 there. Okay, so the set of all network coding solutions consists of all network coding solutions for all positive integer value of this lambda. So lambda can take any natural number here. And now we can define for each of these network coding solutions its rate, and then of course zero error capacity. Okay, so now let's again, as I said, we want to simplify problem bit. So you recall that network coding problem was defined by demands DIs. So if we just let this all DIs 1, then the problem is called a symmetric or concurrent rate. So now we will focus on symmetric or concurrent rate to simplify the model here. So just to summarize, we have seen that the encoding functions, then decoding functions, then network model has this assumption that sources are independent, and then there are edge capacity constraints, and there is a constraint on a rate. So all these constraints can be translated into in terms of this entropy functions. So we know that the random variable or a message that's passing through an edge has to be computable from the random variable that's our source random variables available at the tail node of that edge, as well as the random variables are flowing from edges that are incoming to that edge. So that basically means that this conditional entropy has to be 0. Then again, decoding constraint, we have a 0 error decoding here, so that at each sync, the random variable, source random variable, is reconstructible by all the random variables or messages that are incoming to that node. Okay, then network, this source independence is the basic constraint for our network model. Then edge capacity constraint. So bidirected version we are talking about. So for that, the entropy of random variable flowing in this direction from U to V, and plus entropy of random variable flowing in another direction from V to U. So that cannot exceed. So capacity here we are just considering as unit capacity, and this log B term comes from the network coding solution. So that is the normalizing parameter here. And a symmetric rate R is less than or equal to the entropy of source random variables divided by log b. So I'm using this small h for entropy. Usually it's used as a capital H, but we are using this function so many times, so small h is a little easier on ice. Okay. Okay, so now that we have seen network coding, it's what network coding is, it's mathematical model. So now we will see some inequalities, information inequalities. Some of you may already know basic, some of these inequalities are followed by all random variables, and there are other inequalities we will see in the next slides. So those are specific to undirected network model. So this one, perhaps you can easily recall that in basic information theory, the conditional mutual information is always non-negative, correct? So that is same as submodularity. So it is also called submodularity. So if we consider two sets of random variables, A1 and A2, then h of A1 plus h of A2 is greater than or equal to h of A1 union A2 plus h of A1 intersect A2. So here, for example, if we let A1 as x1 and x3 and A2 as x2 and x3, then it basically gives this submodularity. These two are the same thing. That's what I want to say. Okay. So there is another inequality called n-k-way submodularity. Now, this is not something new type of inequality. It is actually implied by this submodularity inequality. But in a sense, it looks like a generalization of the submodular inequality. So here we are considering two sets. So let's consider n sets. So if we have n sets of random variables, then we first define this sort of sets. So I is a parameter that is runs from 1 to n, so it can take any value, and that basically decides subsets that we are considering, a subset size of the subsets we are considering from this index set n. Okay, so once we fix I, then we collect all a subset of this index set n that runs from 1 to n, and we intersect for all those subsets. We get this quantity first for all such zetas, and then we union over all those zetas. So then we get this value. This is a set of or subset of random variable, which is B.Eng. So once we have this, then this is the n-k-way submodularity. So basically, it says that this sum of this h of ai is greater than or equal to sum of h of B.Eng. I is equal to 1 to k. So if we let here n and k as 2 and 2, then we get this one. So in that sense, this is generalized. This is a generalization of this inequality. However, it is not some non-Shannon type or some new sort of inequality. It is just a basic inequality of information that of entropy function that you know. Okay, so these are inequalities that follow for all random variables, and here we have inequality for a network model, our undirected network model. So that, of course, as you remember, we have converted undirected network into a bidirected version of it. So for that, we have this inequality. So again, first we have two notations, very simple notation. This S V prime means set of all sessions such that SI is in V prime, and ST V prime is that set of all sessions such that either SI is in V prime or TI is in V prime. So given we have, once we have this notations, then we have we can discuss the input output inequality. So input output inequality for information flow for some given node set V prime in this bidirected version of undirected network. So it's described in this manner. So just try to understand this by example again. So let's consider V prime to be this set, this node S1, this node. So it's just a singleton. So then the right hand side for this inequality is basically this Y as V prime is just Y1, and this are the set of all edges from V prime complement to V prime. So these are these edges, this edge and this edge. And the left hand side of this inequalities, so again this is just Y1, and this one is the set of all edges, all these edges. So this inequality is obtained for this undirected network flow problem. And there is another inequality called crypto inequality. Again, so this is a very, again, we try to understand first by cut. So a cut is a non-empty bipartition of V. So V prime and V prime complement, making sure that both are non-empty. And undirected cut set associated with this is denoted this way, and it is basically set of all edges such that U is in V prime and V is in V prime complement, or U is in V prime complement and V is in V prime. So once we have this idea of directed edge, we can define crypto inequality. So that is basically this inequality, and what it says. Again, let's try to understand with the same set. So let's consider this V prime as this node. Then the right hand side basically is this set of all these edges, these four edges, entropy of. And then the left hand side, we have that this edge is basically separate the source and sink of session 1. So then that is Y1, and this is again all these edges. Okay, so these are inequalities that are useful, that we have used also in our results. So that's and it has very interesting results. There are even generalization of these inequalities that you can look into the literature. Okay, so now let's see a couple of bounds on the undirected network information flow before we go to our results. So first bound is the sparsest cut bound. So what is the sparsest cut bound for undirected networks? So it is basically minimum of all sparsity of over all edges. So what is a sparsity? So sparsity is just defined as minimum of the cardinality of that edge set divided by the set of cardinality of set of sessions that are separated if we remove those edges. So that is the sparsity of edge set. So if we find that if we minimize this quantity over all possible E primes, then we get the sparsest cut bound. So as I said, if you remember that we cannot send in butterfly network, I said in undirected case, we cannot send over 1 bit of information, even if we want to do network coding. So sparsest cut, you can see that this, if we remove these edges, then basically it will separate all sources from sinks. And if you compute this quantity, it is just 2 by 2, that is 1. So 1 bit is the upper bound for information flow in this network. Okay, so another upper bound is the linear programming bound. So linear programming bound is simply that random variables are involved. Now, if we collect all basic inequalities as constraints, and if we formulate as a linear program, because these inequalities are linear, and the constraints will also be linear because they are functional dependence or source independence, this sort of constraints are there. So if we want to formulate that, then the number of variables in this LP are exponential in terms of number of random variables involved in the problem, and also constraints are also exponential, a number of constraints. So basically this bound has a formulation. I mean, in theory we can we have this, but it is not computable even for small network. So even for, there is open problem for even smallest network that is of size with a node set that is of size 7 node network, for which this LP is not computed yet. Okay, so it is a good bound, but then we do not have computational resources to compute it in its present form. Okay, so so far we have seen some background, and that was my main purpose, that you understand the problem well, and also you get interested in what the work is done here and why this problem is of interest. And then we will see some results now. So again, let me know if you have any questions. Okay, yeah. So now we present some of the results. So first, to present the results, we need some basic ideas from graph theory. So one is the n-partite graph. So I hope you know that what the n-partite graph is. If not, just let's see that. So a graph which is described by set of nodes and set of edges, it is n-partite if V can be partitioned into n independent sets P1 to Pn. So if we can do that, then it is n-partite graph. And what is independent set? So a set is a set of subset of node set is independent set if there are no edges between the nodes in that subset. Okay, so now this partition into independent set, that we call as partition, and this subsets are called partition sets of P. Okay, so once we have this idea in for this graphs, we can then use that for undirected network model as well. So we can extend that n-partite network and idea of that for undirected network model that we are looking into. Again, there is one notation we have here. So it's simply this is just a subset of sessions such that SI is in V prime and TI is in V double prime, or TI is in V prime and SI is in V double prime. So that is this notation. So once we have this, let's see one. This is one network that is, this is just a graph. Once we assign some sourcing pairs to the nodes, we get a network, and also we assign capacity to edges, then we can translate the graph into a network, undirected network. So here this is a three-partite network. If, as you see, this we can consider as a one partition because there are no edges between nodes. This is another partition, and this is the third partition. Okay, so now let's see one result that is for bipartite network. So we have generalized this result. So it says that for bipartite undirected networks, the symmetric network coding capacity is upper bounded by this expression. Again, it uses this inequalities that we have discussed, this crypto and this NKV submodularity and input-output inequality, this sort of inequalities. So we generalize this. So first, we can first generalize it for three partite networks. So we have generalized it, and we have given two proofs for this. So the first proof uses submodularity. It is lengthier proof, but it is instrumental in improving bound. So we have it is a lengthier proof, but first thing is that this bound is not tight for all networks. Otherwise, we have capacity in general case. So it is not tight. So, but given this network, I mean, given this proof, we can make some modifications such that we can improve the bound. And the second proof, so that does not use submodularity, and it is simpler, but it's not useful in improving the bound. So that these are two differences. However, proof 2 is extendable for n-partite networks. So this first proof, if we try to generalize from 3 to 4 partite networks, 4 to 5 partite networks, the proof gets more and more complicated. Okay, so it doesn't look in the present form, doesn't look generalizable. But proof 2, we can generalize for n-partite. So that's what exactly we did. So we have generalized that. So this is a bound, information theoretic bound for any network. So n-partite network, so to say, and it has this expression. Yeah. And as I said, for this, we have considered that we have simplified model that age capacities are unit and demands are symmetric, meaning 1. But this can be generalized easily for arbitrary demands and arbitrary age capacities. So this is the generalization of that, which is very simple to do. Okay, so now let's talk about computing this bound. So for what we need to do to compute this. So this is of course just cardinality of edge set. This is of course just cardinality of session set. So we want to find out this term. So we want to maximize this term over all possible partitions of the node set into independent sets. So it turns out that that problem is not easy. So let's say we have some partition, such optimal partition, okay, and opti, let's denote opti, the cardinality of opti as the cardinality of those sessions such that source and sinks are in the same partition. Okay, so if we denote that, so basically if we compute this quantity, then we have computed the partition bound. But it turns out that it is not easy to compute this. Okay, so we have a decision version of this problem of computing this. So that is called optimal pairs decision problem. So for undirected network, is opt I cardinality at least k. So this problem, we show that it is an NP complete problem. So we showed reduction from the well-known independent set problem to this problem. So it is hard to compute. And of course, as I said, sparsity, the LP bound is hard to compute, exponential complexity it has because of the formulation itself. And then sparsity's decision version is also shown to be NP complete. So there is no bound that is non-trivial at the same time easily computable for this undirected network information flow problem. Okay, so once we have done, we have this partition bound. Now, one natural question is that for what set of networks this bound is tight. So there was an idea of type 1 and type 2 network given for bipartite network. So we have generalized it. Again, but this is generalization of that network. Definition is a generalization. But we prove that for this network classes, partition bound is tight and achievable by routing. So the proof itself is not a generalization. So type 1 n-partite network. So that is a complete n-partite network with a partition sets Pi, such that for every unordered pair in a partition set, there is a sourcing pair. So this, just recall that this is the tripartite graph we have seen before, and here we are assigning sourcing pairs, and then this becomes a type 1 network. So a theorem that says that for this network, the partition bound is attainable by routing, and hence the conjecture holds for this class of networks. There are infinite networks, such networks in the class. Again, so the proof is by induction for this case. And then another network class is type 2 network. So again, it's n-partite, complete n-partite, but rather than having a sourcing pair for each pair of nodes in a partition set, now we have sourcing pairs for each pair of nodes in the whole node set. So there are extra sourcing pairs here. So proof of it is quite simple, and we have just so we have used proof for type 1 network, and then we have superimposed flows to prove this conjecture for this network. And the third is n-layer network. So of course, for n-layer we haven't proved, we have proved for 3 layers. So n-layer, complete n-layer network is just that we have layer of networks, and each node in layer I is connected to the node in layer I+1. So that is the basic idea of that. So it looks like this. So this is just a graph. Now if for each pair of nodes in a layer, if we assign sourcing pairs, then it becomes a type 1 n-layer network. So for type 1 3-layer network, the conjecture again is true. And I mean, we have a routing scheme that achieves the partition bound. Okay, so now another important result is that recently it was shown that the authors have characterized set of class of networks such that the conjecture holds. So they have shown that, and that all the networks for which the conjecture was known to be true before, all those networks are elements of this class. So in that sense, it's a very interesting and important result. So now the question is, are these type 1, type 2 networks in the same class or not? If they are in the same class, then of course they are important results because we have explicit capacity characterization. However, the conjecture is proven by this result as well, though we cannot have capacity characterization. So for this case, what we show is that we show type 1 network such that it's not in this class. So then it means that we have now networks which are outside of this class of networks for which conjecture is proved before. Yeah, so this ends basically some of the results, and then let's see future directions. So of course, one important interesting question is, can we just characterize, can we just know the set of all networks for which partition bound is tight? So once we have that, then we can focus on the complement of it, I mean all other networks, and then see how we can improve the partition bound or tighten it so that we can have a capacity characterization for even broader class of networks. Then of course, as I said, opt-I cardinality, that is NP decision version is NP complete. So now idea is, can we have some algorithm that computes this quantity? And of course, it has to be better than the brute force method. And another problem is about approximability of this parameter. So does there exist efficient algorithm to approximate this parameter, given that we have some approximation guarantee? So these are some of the future directions in this work, and I thank you all. And one announcement is that JTG IEEE Information Theory Society Summer School 2022 will be organized, will be hosted by IIT Mandi, and we are organizing it. So I welcome you all, and I hope to see you here in the summer time. And if you have any questions later on, you just email me and we can discuss those. So now I hand over, and yeah, it's open for questions. Thank you. Thank you for your patience.
Thank you, Dr. Satyajit, for an informative talk. Are there any questions?
Okay. So there does not seem any questions right away, but if you have any moment, just email me, and then we can have a discussion on that. Okay. Thank you.
So if there are no more questions, then let's end the session. Thank you, Dr. Satyajit, once again. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the web page. Thank you and have a great evening.